Hello and welcome to Pre-Algebra Lesson 25. In this video, we're going to learn about factoring whole numbers. So the lesson objectives for today, we want to learn how to determine if a whole number is prime, composite, or neither. And additionally, we want to learn to write a whole number as the product of prime factors. All right, before we get into factoring whole numbers, let's think about the concept of a prime number. So we have that a prime number is a whole number larger than 1 that is only divisible by itself and 1. So first, let's think about the whole numbers again. So we've talked about these a lot in this course. So let me write out the whole numbers here. And then basically, I'm going to start with the smallest whole number, which is 0. And then we increase in increments of 1. So next comes 1, then 2, then 3, then 4. And of course, at some point we have to stop. We can't list all the whole numbers. So I'm going to put a final comma and then the 3 dots here to show that the pattern continues forever. When we think about this definition, a prime number is a whole number larger than 1. So automatically, I've got to go into these numbers here, and I've got to basically say, okay, I'm only looking at the whole numbers, starting with 2, and going to the right, or starting with 2 and anything that's going to be larger. So it has to be divisible by only itself and 1. We know that every non-zero number is divisible by itself. So a non-zero number divided by itself will always give you 1. So 2 divided by 2 is 1, no remainder. We also know that every number is divisible by 1. If you divide a number by 1, you just get the number. So for example, 13 divided by 1 is 13. So when I think about, let's say, the number 2, that's going to be a prime number because it's only divisible by itself. 2 divided by 2 is 1, and 1. 2 divided by 1 is 2. In each case, you get no remainder, but there's nothing else you can really do with the number 2. So for that reason, 2 is a prime number. And we're going to find that 2 is the only even prime number. So that's really important. Any even number larger than 2 is going to be divisible by 2, and therefore not a prime number because it would be divisible by something other than the number itself and 1. All right, it might be extremely helpful to memorize the first few prime numbers. So I have here the first 10 prime numbers. We have 2, that's the smallest prime number. And then we go to 3, 5, 7, 11, 13, 17, 19, 23, and then 29. So that's the first 10. There's an infinite number of prime numbers, and how many you want to memorize is up to you, but just doing the first 10 will greatly speed up your work in many cases. All right, so how can we check to see if a number is prime? So we're going to use the divisibility rules up to the square root of the number. All right, let's briefly touch on the concept of a square root again. So something like the square root of 64 is equal to 8 because 8 times 8 is 64. When I ask for the square root of a number, remember there's 2 different notations. The first one is the principal or positive square root of, in this case, 64. I am asking for what positive number, when multiplied by itself, gives me this, what we call radicand, or number under the square root symbol. Since 8 times 8 is equal to 64, the square root of 64 is equal to 8. And again, this is the principal or positive square root. If you want the negative square root, you need this notation here. So this is the negative of the square root of 64, and that equals negative 8. So this is asking for what negative number, when multiplied by itself, gives me the radicand, or number under the square root symbol. So since negative 8 times negative 8 is going to give us positive 64, the negative square root of 64 is going to be negative 8. So in this lesson, I'm only going to ask for the principal square root, so don't worry about this negative answer here. So if I asked you for something like the square root of 4, you're just going to answer 2. If I said, what is the negative square root of 4, which I'm not going to do in this lesson, that would be negative 2. Now, the reason it's important to understand about square roots, when we look at the factors of a number, and of course this is just going to be with positive factors, we would have something like for 64, 1 times 64, then 2 times 32, then 4 times 16, then 8 times 8. Now 8 is the square root. And what's going to happen is after this, you're going to have factors, but they're going to repeat. So in other words, the next one would be 16 times 4. Then you would have 32 times 2, and then you'd be back to 64 times 1. So this one right here and this one right here, those are just reversed in terms of the order. Same thing for this one, and then this one and this one. So you basically have duplicates after you hit the square root of the number. Now, in most cases, you're not going to get an integer answer when you take the square root of a number, so we're going to talk about that here. All right, so what if I asked you, is 103 a prime number? So to figure this out, we would need to use our divisibility rules up to the square root of 103. But you might stop for a minute and say, well, what is the square root of 103? I know that something like the square root of 100 is equal to 10, because 10 times 10 gives me 100, or here I've written that 10 squared is 100. Then the square root of, let's say, 121, I know that's 11, because 11 times 11 is 121. When we think about a number like 100 or 121, it's called a perfect square. So a perfect square is a number that can be formed as, let's say, an integer times itself to give you that number. So here, 100, we could form it as 10 times 10, or you could also do negative 10 times negative 10, but let's not worry about that for right now. Then for 121, we could do 11 times 11. So that's why it's a perfect square. Later on, you'll hear about something called rational numbers, and you will extend that definition to say that a perfect square is any number where you could basically take a rational number and multiply it by itself to get the number. But in this case, we're just dealing with integers, so we're just going to go with a simpler definition. Now, 103 is not a perfect square. There's no integer that I can multiply by itself to get 103. So if I say, what is the square root of 103? I'm kind of stuck. But really what you would want to think about is 10 squared is 100 and 11 squared is 121. Well, okay, this number right here is between these two perfect squares. In other words, writing this as an inequality, I could say 103 is greater than 100, and it's less than 121. So if I take the square root of 103, it should be greater than the square root of 100 and less than the square root of 121. Let me actually get rid of this for right now. So if I think about this, I'm just going to drag this up here. This would be that 10, which is the square root of 100, is going to be less than the square root of 103, whatever that ends up being, which is less than the square root of 121, which is 11. So just thinking about this, I can say, okay, well, this would be 10, and I know we haven't gotten to decimals yet, 10 point something. Okay, so it's going to be between 10 and 11. I don't really care what comes after that decimal point. I only care that it's going to be between 10 and 11, and I'm just going to go with that lower integer value. So I'm just going to go with 10. So I would check up to that. If you're lucky and you can use a calculator and you punch this in, you would get about, and I'm going to round this to the nearest hundredth, and we haven't talked about that yet, but I'm just going to put 10.15. So we haven't talked about decimals. We haven't talked about rounding decimals. Just trust me for right now that this is the answer. So it's about 10.15. You can see that that would be greater than 10 and less than 11, but you really don't need any knowledge of decimals. You're just going to, if you're using a calculator, cut this part off and just take that whole number. Just take that 10 and you're going to check up to whatever that is. Okay, so now that we've established that we're going to check up to 10, we can just run through the divisibility rules. For this one, it's going to be actually pretty quick. So we know that this is an odd number, so immediately you can mark out 2, 4, 6, 8, and 10. Then when you think about divisibility by 3, you sum the digits. So 1 plus 0 plus 3. 1 plus 0 is 1, plus 3 is 4. So you think about, is 4 a number that's divisible by 3? No. 4 divided by 3 would give you 1 with a remainder of 1. So because there's a remainder there, you can mark this out. And then if a number is not divisible by 3, it can't be divisible by 9, so mark that out. So now we're left with 5, which is pretty easy, and then 7, which is a little bit tricky. So 5, you just look at the last digit of the number. Is it a 0 or is it a 5? In this case, it's a 3, so 5 is out. So cross that out. And then we think about 7, which is the most challenging. We would think about cutting off the final digit of the number. So in this case, that's 3, so you just cut it off. And then basically over here, I'm going to double it. So 3 times 2, and you're going to subtract that away. So this would be what? 3 times 2 is done first. So that would be 6. So you get 10 minus 6, which gives you 4. So if this number is 0, or some number that's divisible by 7, then basically the number you were working with is divisible by 7. Here, this is a 4, so that's obviously not 0, and it's not going to be divisible by 7. So this will not be divisible by 7. So let's go ahead and say that this number, 103, is a prime number. Now you can see how much work it is to actually go through and check and see if something is prime. So in most cases, your teacher is going to give you something from a list that you've already memorized. But in case you get something that's not, you can go through and use this strategy to determine if something is prime. All right, now let's think about a composite number. So a composite number is a whole number that is greater than 1 and is divisible by a whole number other than itself and 1. So when we say it's a whole number that is greater than 1, again, it's the same numbers that we're working with. We write out the whole numbers, and then basically we start with 2, and then we move to the right on that list, or you say anything that's 2 or larger, that's what you're thinking about. So it's got to be divisible by a whole number other than itself and 1. So here are the first 10 composite numbers. So when you look at 4, 6, 8, 9, 10, 12, 14, 15, 16, and 18, notice that 4, 6, 8, 10, 12, 14, 16, and 18, those are even numbers. Again, they are automatically going to be divisible by 2 because they're even numbers, so they can't be prime numbers. They're automatically going to be composite numbers because they are divisible by some whole number other than itself and 1. So now looking at the other ones, we have this 9 here. 9 is divisible by 3. You have 15. 15 is divisible by 3 and also 5. And that's pretty much it for the first 10 composite numbers. Obviously, there's an infinite number of composite numbers, just like there was an infinite number of prime numbers. You can't memorize all of them, so you just have to go through the strategies to determine if you have something that's prime or composite. All right, now on your test, you might be asked about 0 and 1. Remember, in the definition for a prime number and also in the definition for a composite number, we specifically said it was a whole number larger than 1. So basically, we're starting with 2 and we're looking for anything larger. So what about 0 and 1? The numbers 0 and 1 are not prime, so they're not prime, and they're also not composite. If you get that question on a test, they are neither. Okay, you want to put that down. They are neither. They're not prime and they're not composite. All right, let's run through a few of these. So we want to determine if each number is prime, composite, or neither. We're going to begin with 123, and coming down here, you see that I have some numbers listed here. So starting with 2 and then going up to 11. So why did I stop with 11? Remember, we only need to check up to the square root of the number. Now, in this particular case, 123 is not what we call a perfect square. There's no rational number, or some books will say integer, that multiplies by itself to give you that number. So when I have this situation, I'm going to think about the fact that 11 squared is going to be 121. And then 12 squared is going to be 144. So these are things that I know. If you don't, you can do a multiplication. So if you're not using a calculator, you're just going to think about the fact that, okay, well then the square root of 121 is 11, and then the square root of 144 is going to be 12. Well, this number 123 is going to be between those two numbers. In other words, 123 is greater than 121 and less than 144, so then the square root is going to be somewhere between 11 and 12. I don't actually care where it is because I'm just going to go down to 11, right? So I only have to check up to 11. If your teacher is nice, then it's a lot quicker. You can just say, what is the square root of 123 in your calculator? And we're going to approximate this. And I get, if I round to the nearest hundredth, about 11.09. Okay, so about 11.09. And again, just cut this part off. Just get rid of this and just take the whole number part. And basically, I'm going to check up to 11. That's all you need to do. So looking at this, I know that this is an odd number. So immediately, it's not going to be divisible by 2 or 4 or 6 or 8 or 10. Okay, get rid of that right away. Then when I think about 3, well, this number you would sum the digits. 1 plus 2 is 3. 3 plus 3 is 6. Well, yeah, 6 divided by 3 is 2, no remainder. So yeah, immediately I know this is a composite number. So this is a composite number. What about the number 51? Again, if I'm thinking about the square root of 51, if I'm lucky and I have a calculator, well, I would say that's about 7.14 if I round to the nearest hundredth. So I only need to check up to 7. Again, if you don't have a calculator, then just think about the fact that 7 squared is 49, and then 8 squared is 64. So if you think about this, get rid of this for a moment, we know that 51 is greater than 49 and less than 64. So that means when I take the square root of 51, I'm going to get something that's between 7 and 8. I don't actually care what it is. I know that I'm just going to go down to 7. So checking this, I need to look at 2, 3, 4, 5, 6, and then 7. So just going up to 7. This number's not even, so you can immediately get rid of 2, 4, and 6. And then just think about, is it divisible by 3? 5 plus 1 is 6. 6 divided by 3 is 2, no remainder. So yeah, this is going to be a composite number. All right, what about 59? So again, I can take the square root of 59 in my calculator if I'm lucky, and that would give me about 7.68 if I round to the nearest hundredth. Or if I don't have a calculator, I can think about the fact that 7 squared, again, is 49, and then 8 squared is 64. So the square root of 59, because, again, 59 is greater than 49 and less than 64, it's going to be between 7 and 8. Again, I don't care about this 0.68 part. I only care about the whole number, so I only care about that 7, just going down. So I want that 7 there, so I only want to check up to 7. This is not an even number, so I can get rid of 2, 4, and 6. Think about 3. 5 plus 9, that's going to be 14, so you can get rid of 3. 14 is not divisible by 3. Now for 5, again, the final digit has to end with a 0 or a 5. This does not end with a 0. If it did, it would be an even number. And it does not end with a 5. So let me get rid of that. So now we have to check 7. For that one, we know the rule is a bit complicated. It might actually be quicker to just do a division. But what you do is actually cut off the final digit of the number and you double it. So 9 times 2. And you subtract that away. So basically 9 times 2 is 18. So this would give me 5 minus 18. And this would give me negative 13. And forget about the fact that it's negative. Just say, is 13 divisible by 7? The answer is no. So you can cross this out. And then we can conclude that 59 is going to be a prime number. So it's only divisible by itself. So 59 divided by 59 is 1. And then also 59 divided by 1 is 59. All right, now let's actually move into factoring whole numbers. So I'm going to start off with a basic definition that of course we already know, but I want you to recall that 2 or more numbers that are multiplied together are known as factors. So in this multiplication problem, 3 times 5 equals 15. The 3 and the 5 are known as factors. They're being multiplied together. The 15, the result of the multiplication operation, is the product. Then 8 times 7 equals 56. The 8 and the 7 are the factors. The 56 is the product. So when we have factors that are prime numbers, they are known as prime factors. Now, a lot of times you're going to be asked to find the prime factorization of a number, and that just means you're going to break the number down into the product of prime factors. So I have here that it is often useful to write a number as the product of prime factors. We're going to have a lot of operations moving forward that are going to depend on this knowledge. So I have here to write a number as the product of prime factors, we continue to factor each factor until it's prime. So I'm going to start off with this 80 here, and then I'm going to show you how to do this with a factor tree, which is a great way to visually organize your work. So here I have, let's try to write 80 as the product of prime factors. So I'm just going to start off with 80 is equal to, just pick any 2 numbers other than itself and 1. So I'm not going to pick 80 and 1. I'm going to pick something like, let's say 8 and 10. So 8 times 10. And then just keep breaking these numbers down. So 8, I know that's 4 times 2. 2 is a prime number. And then times, for 10, I'm going to put 5 times 2. So 5 is prime and 2 is prime. But I can break 4 down and say that's 2 times 2. So then times 2 and then times, let me reverse the order here. So put 2 there and then times 5. So what do I have? I have 1, 2, 3, 4 factors of 2. So let's say this is 2 to the 4th power. And then times 1 factor of 5. So 2 to the 4th power is 16, and 16 times 5 is 80, right? So we've basically broken this down into the product of prime factors. And again, you're going to need to do this a lot moving forward. So this is the process you could use. Using a factor tree is generally a little bit better because it helps you to organize your work. This right here is kind of a mess and not organized. So in order to use a factor tree, you want to write the number to be factored and extend 2 lines below. So these lines that you're extending below, they're going to basically be called branches. Then you want to list any 2 factors of the number. So then other than the number itself and 1, and you're going to place each under one of the lines or what we call the branches. Then we're going to circle any prime factors. And for any factors that are not prime, we just repeat the process. So you're going to extend 2 branches, list any 2 factors other than the number itself and 1, and then you're going to circle the prime factors. So I have here, this continues until all factors are prime. Okay, let's look at some examples. We will look at 80 again using a factor tree. So let me write 80 here, and then these are going to be my branches. So you can do anything other than the number itself and 1. So before we did 8 and 10, let's change that up and do 16 and 5. So now, once you've listed 2 factors, check to see if one of them is prime. 5 is prime, so you're going to circle it and you're going to stop. For 16, it's not prime. I could say this is 4 times 4, and then you're going to check neither of those is prime. And so this is 2 times 2, and then this is 2 times 2. And so you're going to circle these. So this, and this, those are all prime numbers. So this gives me that 80 is equal to 1, 2, 3, 4. So 2 to the 4th power times 5. Now let me do this a different way just to show you that you get the same result. Let's say I didn't start with 16 and 5. I could have done 8 and 10. So let's say I do 8 and 10. And so this, neither of those is prime. So I'm going to go 5 and 2. 5 and 2 are both prime. So I'm going to circle and stop. And then for 8, let's go with 4 and 2. And then 2 is prime, so circle that and stop. And then for 4, it's 2 times 2, so circle those and stop. So basically you get 2 times 2 times 2 times 2, which is 2 to the 4th power, and then times 5. So same thing either way. Let me just do it one other way just to show you that it doesn't really matter. So I'm going to go 4 and 20. Okay, so 4 is 2 times 2, and we're going to stop, right? So this is prime and this is prime. 20 is 4 times 5. 5 is prime, so we're going to stop. Then 4 is 2 times 2, circle those, and stop. So no matter how you do this, you end up with 2 times 2 times 2 times 2, which is 2 to the 4th power, times 5. Okay, let's look at 95. So 95. So for this one, you might think about, okay, how do I get started? 95 is not something I really work with that often. If you notice the number ends with a 5, you know it's divisible by 5. So I would come over here, if you don't have a calculator, and just do a quick long division. 5 goes into 9 once. 1 times 5 is 5. Subtract 9 minus 5 is 4. Bring down this 5 here. 5 goes into 45 9 times. 9 times 5 is 45. Subtract and you get 0. So I could do 19 and then 5. So let me get rid of this. And we know 5 is a prime number. What about 19? Well, I did list this as one of the first 10 prime numbers. If you didn't know that, again, you can go through the process we talked about earlier in the lesson, and you could check and confirm that this is a prime number. So this right here, 95, would be equal to 19 times 5. What about 240? 240. So if a number ends with a 0, it's divisible by 10. Usually that's the easiest to start with. So I'll just say this would be 24 times 10. So then from here, I know that neither of these is going to be prime. So this right here would be 5 times 2. Circle these. 5 and 2 are both prime. For 24, a lot of different things you could do. You could do 4 and 6. You could do 8 and 3. You could do 12 and 2. Whatever you feel like. Let's just go with 4 and 6. So neither of those are going to be prime. So 6, I'm going to do 3 and 2. And this is going to be 2 and 2. Let me circle this and this and this and this. All of those are prime. So 240 would be equal to 1, 2, 3, 4 factors of 2, so 2 to the 4th power, and then times, you've got 1 factor of 3, and then times, you've got 1 factor of 5. Now, let's say, just for the sake of completeness, I get rid of this, and I would have started with, let's say, 20 times, let's say, 12. I'm just showing you it doesn't matter how you start. So 20 and 12, neither one is prime. This one, you could do 5 times 4. 5 is prime. 4 is 2 times 2. 2 is prime, and 2 is prime. 12, you could do 4 times 3. So 3 is prime, 4 is 2 times 2. And again, you get 1, 2, 3, 4 factors of 2, 1 factor of 3, 1 factor of 5. So it doesn't matter what you start out with. Just pick any 2 factors other than the number itself and 1, and you're going to be good to go. Just keep going down and breaking each number down this way. All right, what about 126? So this number, it's an even number, so I know it's divisible by 2. And then 1 plus 2 is 3, plus 6 is 9. So that tells me it's divisible by 3 and also 9. But because it's divisible by both 2 and 3, it's going to be divisible by 6. Let me do that off to the side. So 126 divided by 6. 6 does not go into 1, but it will go into 12 twice. 2 times 6 is 12. Subtract, you get 0. Bring down the 6. 6 goes into 6 once. 1 times 6 is 6. Subtract, and we get 0. So basically, you could do 21 times 6. So this would be 21 and 6. Now 21 and 6, neither of those is going to be prime. 6 is going to be 3 times 2. Let's circle these. 3 and 2 are both prime numbers. 21 is 7 times 3. Let's circle those. 7 and 3 are both prime numbers. So let's say 126 would be equal to, let's go 1 factor of 2, and then times, we have 2 factors of 3. So let's say 3 squared, and then times 1 factor of 7. All right, what about 828? So it's kind of a big number. I know it's an even number, but I would look at the last 2 digits here. This is a 28, so this number is going to be divisible by 4. And I would also check and see if it's divisible by 3. 8 plus 2 is 10. 10 plus 8 is 18. So it will be divisible by 3 and also 9. Now, if a number is divisible by both 3 and 4, it's going to be divisible by 12. So I'm just going to start with that. So 828 divided by 12, and you could do something else. It's really up to you. So 12 goes into 82 how many times? Well, I know that 6 times 12 is 72. So let's put a 6 here. And 6 times 12 again is 72. Let's subtract. 2 minus 2 is 0. 8 minus 7 is 1. So this is 10. Bring down the 8. So 12 goes into 108 how many times? Well, from the multiplication tables, that would be 9. Because 9 times 12 is 108. So we'll subtract here and get 0. So I could go 69 times 12. 69 times 12. And again, you could have started with something else. It's really up to you. So for this one, I'm going to go 4 and 3. 3 is prime, so let's circle that and stop. 4 is 2 times 2. Those are prime. Over here for 69, let's think about that for a moment. So it's not an even number. And 6 plus 9 is 15, so this is divisible by 3. So let me start with that. So 69 divided by 3. 3 goes into 6 twice. 2 times 3 is 6. Subtracting, you get 0. Bring down the 9. 3 goes into 9 3 times. 3 times 3 is going to be 9. Subtracting, you get 0. So this would be 23 times 3. Let me get rid of this. So hopefully you remember that 23 is a prime number. That was in the list of the first 10 prime numbers. And 3, of course, is a prime number. Again, if you don't know that 23 is a prime number, you can quickly find that out using your divisibility rules, going up to the square root of the number. So let me write out that 828 is going to be equal to, we have 2 factors of 2, so 2 squared. Let me slide this down just a little bit here so it fits. And then times, and then you have 2 factors of 3, so 3 squared. And then times, you're going to have this 23. Let's do one more, and this is a really big number. Usually you get numbers that are at most 3 digits, but I'll do one with 4 digits just so you get some practice. So 4,320. Again, this ends with a 0, so it's not that bad. I would just start by saying, okay, well, this is going to be 432 times 10. And then for this one, this is 5 times 2. Circle these. You're done over there. So now you got to think about 432. So I know immediately, looking at the final 2 digits, that this guy right here, since 32 is divisible by 4, 432 will be divisible by 4. So you could start with that. But then again, if you look at 4 plus 3, that's going to be 7. 7 plus 2 is 9. So this number is also divisible by 3 and 9. Okay, so if it's divisible by 4 and 3, you can go with 12. There's other things you can do, but I'm just going to go with 12. So let's say 432 divided by 12. So 12 will not go into 4. It will go into 43. We're going to do that 3 times. 3 times 12 is 36. Let's subtract. I'm going to borrow here and say this is a 3, and this is a 1. 13 minus 6 is 7, and then 3 minus 3 is 0. So we're going to bring down this 2 here. So 12 goes into 72 exactly 6 times. 6 times 12 is 72. Subtracting, you get 0. So this right here is going to be 36 times 12. All right, for 36, we could do, let's say, 6 times 6. You could also do 4 and 9, whatever you want to do. And then for 6, we could go 3 times 2, and then 3 times 2. So we'll circle these. These are all prime numbers. Then for 12, let's go 4 and 3. I'll circle 3. And then for 4, this is going to be hard to fit. So let me branch down here like this. This is going to be 2 times 2. So let me circle those. Okay. This one's pretty big. Let me actually slide this whole thing over to the left so I can fit it. All right, let me write this 4,320. I'm just going to highlight my 2's. So 1, 2, 3, 4, 5 factors of 2. So this is equal to 2 to the 5th power, then times. So now let me go through with a different highlighted color, and I'm going to look for my 3's. So I got 1, 2, 3 of those guys, just so I don't miss anything. So this is 3 cubed, and then times, you've got that 1 factor of 5. Let me highlight that for consistency here. So I'm just going to put times 5. And you can verify that if you have a calculator, but basically 2 to the 5th power is 32. So this is 32, and then times 3 cubed would be 27, and then times 5. So if you want to punch that into a calculator real quick, you'll see that you do get 4,320. Or of course, you could do a vertical multiplication with these 2 right quick, and then do another one with this one and verify it the long way.